motion. And some of the chips, some of the rock samples are brought to the surface and which have been taken, which could be used to identify the lithology at different depths along the borehole. So talking about invasion, you know, we can see we use a caliper to determine the diameter of the borehole. So we can see the diameter of the borehole here. So we can see it, how expansive it could be. So we can, when we talk about in the process of this drilling, we see that the mud log, what does it do? It helps us to ensure that the pressure within the borehole is maintained, is balanced, is maintained. It also helps to serve as coolant to the drill bits. You know, it serves as coolant to the drill bits, and it also helps to lubricate. But in the course of this drilling, what happens? The mud filtrate, that is the fluid that is mixed with the mud, that's the mud filtrate. You know, when this motion continues, and because of the great pressure difference in the borehole, some of the mud filtrates may find their way, that is the mud fluid now. Some of the mud filtrates might find their way into the formation. You know, we have different lithology variation along the borehole. In a region where we have a porous formation, the formation the zone that is porous, that is permeable, what happens? Some of these mud filtrates can find their way into the formation. And when it finds its way into the formation, it affects the fluid in the formation. So, and we can use our resistivity method to get variation of this flow of current in this formation. You know, resistivity method helps us to measure the resistance or the how the formation resists the flow of current. And we said that we could have a rock that contains fresh water. And we know that these rocks constitute a lot of minerals. And some of these minerals are dissolved in the water, and which makes it to dissociate to anions and the cations. And this helps in carrying the flow of current. So it helps in conduction. And so we can say that when we have high degree of salt concentration, then we tend to have high conductivity. And when we have a low salt concentration, we tend to have low conductivity. You know, we said that we could use the resistivity method for us to be able to differentiate our fluid types. That is it hydrocarbon that we have there? Is it water that we have there? Also, we can differentiate between saline water and fresh water, you know. So our resistivity can really help us in taking these certain measurements. And we know the unit of our resistivity is ohms meter. Okay? So now, this zone could be divided into two. That is, we have the invaded zone and the uninvaded zone. So you can see.
Which zone?
I said invaded zone and uninvaded zone is there. If you look at the slide, is there uninvaded zone and we have the invaded zone. Do you get it now? We have the invaded zone and we have the uninvaded zone. What do we mean by the invaded zone? What do we mean by the uninvaded zone? The invaded zone is divided into two. We have the flushed zone and we have the transition or annulus zone. I hope I'm not too fast.
Maya, too fast, no.
Okay. So like I said, that we have two zones. So we can say we have the invaded zone and we have the uninvaded zone. For the invaded zone is divided into two. We have the flushed, F-L-U-S-H, is the flushed zone. Then we have the transition zone. I hope that is taken. Is that okay?
Yes, ma'am.
Okay. So talking about the flushed zone. So what we're trying to say that in the flush zone, now we have identified the permeable zone. We are talking about the permeable zone, that is the porous zone. So that reservoir, that zone, what happens? We said that the fluid, find its way into the formation because that formation is porous and because it is permeable and because of the influence of the pressure at which the borehole is being drilled. So some of the mud filtrates, finds their way into the formation. This is where the formation, this is the permeable zone, this is the formation. And they now find their way into the formation. So what now happens? We discovered that some of the fluid, the formation has its own fluid. The formation fluid could be oil, could be water, could be gas. So that fluid in that formation now there is another thing that is coming in, which is the mud filtrates. So what happens in the flush zone? All the formation fluid in the flush zone has been completely replaced by the mud filtrates. The formation fluid has been completely replaced by the mud filtrates. That is for the flushed zone.
Can you repeat it again, please?
I said, in the course of drilling, that we drill with our mud, the mud system that keeps circulating in and out. And I said that the mud system usually it has different fluids that could be mixed with. It could be oil, it could be water, fresh water, salt water. So now I said when the mud is being mixed with this fluid, so what the fluid that comes out of it, just like when you wash a cloth and you squeeze it, that when you squeeze the cloth, what happens? The fluid will come out. So the fluid that comes out is the mud filtrate. And that mud filtrate finds its way into the formation because that formation is porous, it is permeable. So it allows the fluid to come in. So I now said that for this borehole environment, we have some region that could say that it has been invaded, and the region that is uninvaded. So the region that is invaded is divided into two. That is the flushed zone. That is the first region, the flushed zone. Then the second region is the transition or the anomalous zone. So this flushed zone, what happens there? As the mud filtrate comes in, what happens? It displaces the formation fluid. That is the fluid in that reservoir. It displaces it at that depth in the formation. So the flush zone is a zone whereby the formation fluid has been completely replaced by the mud filtrates. Do you get it now?
Yes, ma'am.
Okay. So we now have the transition zone. You can see that the transition zone is a bit further away from the borehole. So that region is the transition zone. So this transition zone, we have the mixture of both the mud filtrate and the formation fluid. So we can say that the formation fluid has been partially replaced by the mud filtrate in the transition zone or the anomalous zone. So is that taken?
Yes, ma'am.
Okay. Then we have the uninvaded zone. So the uninvaded zone is a zone that is not disturbed by the mud filtrate. It could be called the virgin zone. That is, it has not been disturbed. The mud filtrate has not gotten to that place. The mud filtrate has nothing to do with the uninvaded zone. Do you get it now? So the formation fluid is still intact in the uninvaded zone. Do you get it now? So we have the flush zone. The flush zone, the formation fluid has been completely flushed out, has been completely replaced by the mud filtrates. In the transition zone, the mud filtrates has partially replaced the formation fluid. But in the uninvaded zone, the formation fluid is not disturbed. So we still have the true formation fluid in the uninvaded zone. Do you get it now? And our resistivity helps us to measure, it will measure the resistivity in the flushed zone. It will also give us resistivity in the uninvaded zone. That is why I said that in our resistivity, we can have shallow resistivity measurement, medium resistivity measurement, and deep resistivity measurement. So the resistivity enables us to measure the depth in the formation. So as a result, we can measure the resistivity in the formation at varying depth. So this enables us to see what the resistivity will be in the flushed zone, what the resistivity will be in the uninvaded zone. And that is where we can get the true resistivity of the formation. And that is where we have our health RT there, which is the true resistivity of the formation. It can give us the resistivity of water. That is our RW, resistivity of water. It can give us, we can be able, from this resistivity, we can be able to estimate water saturation. That is, what is the degree, what percentage of the pore spaces is being occupied by water. Do you get it now? So, and what happens when this mud filtrates get into the formation, it leaves behind the mud cake. Just like I illustrated that maybe when you wash a cloth and you squeeze the cloth and the water comes out, So the leftover is of the mud, accumulates on the walls of the borehole to form the mud cake, which at times reduces the diameter of the formation, which I said from there we can be able to identify the permeable and the non-permeable zones in the formation. So we can see our DH represents the O diameter, our R is resistivity, our RM is the resistivity of the mud, our RMC is the resistivity of the mud cake, that is the mud that is left behind that hardens on the walls of the borehole. Then we have the RMF, that is the mud filtrates. MF represents the filtrate, the mud filtrates. So what is the resistivity of the mud filtrates? Then we have the RX0, that represents the resistivity of the flushed zone. So we use X0 for the flushed zone. And RT, that is the true resistivity of the formation. That's the one that gives us the resistivity of the formation. You can recollect in one of the logs that we looked at then, okay? Here. Is it this one? I think there is another log. Okay, here. So we can see our ILS here. That is the shallow. Sorry. So we can see the shallow resistivity, the medium resistivity, and the deep resistivity. And at times you will see that our deep resistivity is the one that gives us the true resistivity, because it measures the resistivity of the formation that is not disturbed.
Did not mind. Did not mind.
Is that right? Okay, so this is also an example. We have our caliper, we have our gamma ray log. So you can see here we have low gamma radiation.
So you knew when you were mining Ethereum? Do you know when you were mining Ethereum?
So who is this Francis? Francis, mute yourself. Okay. Okay, so we can see that where we have low gamma response, indicating our sand formation, because it does not contain thorium or calcium, it has less of that, so we have low radioactivity at that region, and we can see that's our sand formation. And we check our resistivity log. So we can see our deep resistivity, we can see our medium resistivity, and we can see our shallow. So look at it now. So we can see it now. So we can see the resistivity of the deep is one that gives us the highest resistivity. So we can see that we have very high resistivity in this region, indicating presence of hydrocarbon. Because if it is water, then we're supposed to have low resistivity. It shouldn't be as high as that of hydrocarbon, you know. And here we have our neutron porosity and our density. So we usually log our neutron and density logs together because it can enable us to differentiate the fluid type, the hydrocarbon type rather. Our resistivity log helps us to identify the fluid type. That is it water? Is it hydrocarbon? We use our gamma and our caliper and our SP log to identify the lithology. What kind of lithology do we have there? Is it shale? Is it siltstone? Is it sandstone? You know, and we know that in the Niger Delta we have predominantly shale and sand. You know, so it's a sedimentary terrain, and that is our focus for oil and gas exploration. So we can see that here the area that we have our sandstone here, okay, where we have low gamma radiation, and we can see our resistivity log. Our resistivity log can help us in fluid typing. Fluid typing, that is to identify our fluid type. Is it water? Is it hydrocarbon? Then our neutron density log helps us to predict, that is to differentiate whether it is gas or hydrocarbon. You know, like this region that you have identified that we have hydrocarbon there because of our high resistivity there. So looking at our density and our neutron log, what are they saying? We can see that our neutron log, which is red, you know, drops here, and that is the gas effect. It drops because of the low hydrogen content. So we can see usually it can be wider than this, you know, that can form something like a balloon to show that it is gas. But when it closes up, if you look at uh, the lower zone, it is still sand. If you look at it here, you still have sand here. And if you look at it here, we have low resistivity. We have low resistivity here, telling us that we don't have hydrocarbon here, but we have water. Do you get it now? But if you come and check the neutron density log, you can see that they are closing up. So the gas, the water and the water and oil, they tend to give similar response, closing up in our neutron density log. But our resistivity log can help us to differentiate whether it is oil that we have there or whether it is water that we have there at that particular zone. I think somebody also asked me about the sonic log. That why do we have that we can use it to identify fracture? So you were saying last week that we could use it to identify fracture. Then how come it was stated that not sensitive to fracture porosity? I think it's supposed to be fracture secondary porosity. That is, it can help us, we can use it to estimate porosity. That is the porosity of the rock formation. But maybe due to cracks or other variations that might take place, it might not be able, when we now have cracks in the formation and all that, it might not give us it might not give us precise value to predict our porosity. So in this kind of situation, our neutron density log could also be used to estimate our porosity, which could also be used to correlate with what we will obtain. Now that is why we don't just use one technique, because one technique might have one limitation and the other might have the advantages over the other. So that is why we have to use two or more techniques. And that is why when we talk about the wireline log, you know, the wireline log has to do with measurements, the measurement taken while drilling. It cannot be as detailed as having open logs. You know, while drilling this takes some certain measurements, which can help us to identify that, okay, this is most likely where our prospect zone is. If you can identify where the prospect zone is, do you get it now? Core samples can be taken from there. We know we have different techniques of retrieving our cores from the borehole. Can you tell me some of the techniques that we could deploy to retrieve some of these core samples?
Coring.
Coring, okay. So for the coring, we have different ways. Is it conventional coring, the traditional conventional coring? Is it the sidewall coring? Is it cuttings? What is the limitation of cutting? What is the limitation of sidewall coring? And why is a conventional coring having more, is being widely accepted compared to cuttings and sidewall coring?
I think because some of the structures in the subsurface, after a sample of rock has been gotten, will be destroyed. Like if a sample has been gotten from the subsurface and it had maybe some structures in it, because it has been taken out, some of the structures will be destroyed alongside while it is being removed from the subsurface. So you will not be able to tell the real lithologies or some of the characteristics of the rocks that was taken from the subsurface compared to when you just do coring. I don't know if I'm correct.
So can I shed more light? Any other person? We'll talk about cuttings. Cuttings has to do with while drilling, you know, some of the samples are brought to the surface. And some of these samples are taken and are being put in the cellophane and being labeled and all that. You know, that during drilling, during the drilling, the mud logging, you know, doing that motion, circular motion as it goes in and comes out, some of these cuttings are being brought to the surface. And from there, they can take the samples. That is cutting. But the main issue is that our concern is to be able to get these samples in such a way that is not disturbed, so that the information there will not have been disrupted, so that we can be able to accurately predict the porosity, the permeability, and all these physical parameters. So in cuttings, these chips are brought to the surface, quite all right. But we might not be able to specifically say that this sample is coming from this social depth. You know, while drilling, they might drill 2 meters and stop, take the samples, 4 meters, take the samples. But between that 2 to 4 meters, we cannot say precisely where that chip is really coming from. So we cannot really ascertain the depth at which that sample is coming from. Then we'll talk about the sidewall coring. The sidewall coring, the device is being lowered and is being fired. The wall is being fired using explosive. And some of the samples, the cuttings are being retrieved and brought to the surface. So that could also be used, is also a method of retrieving the core samples to the surface for analysis. But at the same time also, the depth could not be precisely be ascertained. But when you talk about conventional coring, which is very, very expensive, so an open cylinder is attached to the device and it is being lowered down and at that specific depth. That's why I said measurement has to be taken while drilling. They must have identified the depth that is porous, that is permeable, that is most likely to be the prospect zone before they carry out that conventional coring, because it's very expensive. They cannot take samples all through the borehole. So they have to know the specific depths that they want to target, that they want to take the sample from. So, and that one, they are able to take a good amount of the sample, which will now be taken to the lab for analysis. But it's very expensive. That is why they have to be precise. They have to know the depth that they are targeting before they carry out the conventional coring. Okay. So, so like I said, that I will also estimate these parameters, because we could estimate them using our well-logged data. But the essence of coring again is to validate our interpretation, because that is a direct, we can see the sample, we can feel the texture, we can measure directly from there, from the core samples. So we can use what we have from our core to validate what our log data is saying. So we can be able to correlate and see if what we have been able to interpret from our log data is truly what is close to what is being seen in the core samples. Okay. 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 So now, so we can see these parameters being measured. So now, if we want to talk about our petrophysical parameters, so when I talk about petrophysics, what do we mean by petrophysics? We can explain what petrophysics is all about. Anybody?
Is the study of rock properties like permeability, porosity, the effective permeability, and absolute permeability, and how the gases interact, like the how they interact within the void spaces in the rock.
Okay, so it's a study of the physical parameters of the rock and the fluids. So most especially, we carry out this for us to be able to detect and evaluate the hydrocarbon prospects. So it enables us to see how the rock properties interact with the fluid. So from there, we can be able to determine all these parameters and be able to see. Because even if we identify that this is our prospect zone, we discover that it is porous, that it is permeable. You know that it is not even if it is hydrocarbon that is, it's not all the hydrocarbon that is producible. Okay, what amount of the hydrocarbon can we move that is movable? You know, what is the volume of hydrocarbon in place? Yeah, so that for our decision, for economic decision to be taken, it will not make sense that we invest so much money into it, and at the end of the day, what we end up producing is what we spend in producing is now more than what we get that is being exploited. So we have to ensure that the volume that will be exploited, the amount that we're going to, the profits is there. So for economic decision to be taken, if the quantity of the carbon that we have there will not give us much profit, or probably it will not yield for a long period of time, then we might not invest in such. So we have to carry out, measure these parameters. From there, we can do so many calculations to be able to determine the volume in place, to determine so many parameters that can serve as indices for us to know that, okay, truly we have the carbon here. What we have there, the amount is good enough that is exploitable. Okay, we can, what kind of method are we even going to deploy because of the kind of porosity that we have there? What kind of well are we going to do? Is it going to be a deviated well? Is it going to be a vertical well? Is it going to be an horizontal well? Based on the kind of structures, the kind of geologic features that we have there, this can give us idea of how to go about our exploration and how to make our development plans. Okay, so one major factor that we have to also consider is the water saturation. That is the percentage of the pore volume in the rock that is occupied by water. And there is a relationship between the water saturation and hydrocarbon saturation. So we know that our water saturation plus hydrocarbon saturation equals to 1. So if we are able to estimate the water saturation that we have there at that prospect interval, then we can be able to determine the hydrocarbon saturation. So if this is the volume occupied by water, then we'll know the volume occupied by our hydrocarbon. So we just have to subtract our water saturation from 1, then we'll be able to get the hydrocarbon saturation. So I will also have what is known as irreducible water saturation. That is, even if we are exploring for water, or even if we are exploring for hydrocarbon, it's not all that will be producible. Some of them will be held to the grains due to the capillary pressure. Some of it will not be explored. It will not let go. Just like what we have in the cohesive force and the adhesive force. The cohesive force has to do with the force that binds together materials of the same nature. But when we talk about that adhesive, that's to do with different materials. Do you get it now? So it's like, it will be held together and it will not let go. So that is irreducible water saturation. And I think in your last assignment, I gave you that what do we mean by effective porosity? What do we mean by total porosity? Is there anybody that can provide answers to that? What do you mean by effective porosity? What do you mean by total porosity?
My effective porosity is the interconnected pore volume or void space in a rock that contributes to fluid flow or permeability in a reservoir.
That is effective. What about total porosity?
The total porosity is the total void space, which includes the isolated pores and the space occupied by clay-bound water.
Okay, the isolated pores. Okay, to break it down, we can say that the connected and the non-connected pore spaces. Okay, but I discovered that Louisa, you are the one giving answers to most of the questions. Does that mean you are the only student that I have in the class? So response to questions, we have marks for you too. So Louisa is the only person getting all the marks. Hello. What about the effective permeability, effective permeability, relative permeability, and the apparent permeability? So he's going to talk about that. I'm listening.
Good morning.
Okay, morning, Tayo.
Okay, effective permeability. This is the ability to transmit a particular fluid where there are other immiscible fluid in the reservoir.
Okay, that is what? What did you just define?
Effective permeability.
You said?
Effective permeability.
Effective permeability. That is when a formation contains two immersible fluids and one is being transmitted at the expense. Okay, and one is being transmitted at the expense of the other. Okay, that is effective permeability. Okay, so he's going to talk about apparent permeability.
Ma.
Yes.
Okay. Absolute permeability.
Okay.
I think this is the ability of a fluid to flow when there is only one type of fluid in the reservoir.
Okay. When the formation is 100% saturated with only one kind of fluid,
only one type, yes.
which it transmits. So what about relative permeability?
Good morning, ma.
Yeah, morning.
It's
Who
the
is
ratio.
That? Okay, fine. Okay.
I think it's the ratio of effective permeability at a particular saturation to absolute permeability.
Yes, is the ratio of effective permeability to absolute permeability. Okay, thank you. Okay, so now let's talk about water saturation. So according to Archie, so we can estimate our water saturation SW to be equals to root of how W over how T, where our how W is the resistivity of the water or resistivity of the formation water, or resistivity of the formation when filled with water, and our RT is the true resistivity of the formation. Okay, then we have, if you want to estimate the water saturation of the flushed zone, equals to the root of product of formation factor, resistivity of the merged filtrate over resistivity of the flushed zone. And we know that our formation factor equals to 1 all over porosity square. Okay, 1 over porosity square. So, and if we are able to estimate the water saturation, then we can be able to get our hydrocarbon saturation using this formula. You know, like I said, that water saturation plus hydrocarbon saturation equals to 1. So if you want to estimate your hydrocarbon saturation, you just substitute the formula, your SH equals to 1 minus water saturation. Then if you want to estimate the water saturation of a flushed zone, you know, I stated earlier the resistivity, water saturation of the flushed zone could be estimated using square root of the product of formation factor and resistivity of the mud filtrate over the resistivity of the resistivity of the flushed zone. So if you are given parameters that involves mud filtrate, resistivity of the mud filtrate, resistivity of the flushed zone, you are given porosity, then you know that you estimate the water saturation of the flushed zone using this first equation. Using the equation, okay? Using this, where our n equals to 2. Okay, so then we can estimate our residual hydrocarbon saturation. So like I said, that you cannot produce all, some will be left behind. So for you to estimate the saturation of the residual oil hydrocarbon, you use 1 minus the flushed zone, then 1 minus the water saturation of the flushed zone. Then we have movable oil saturation. So if you want to estimate the movable oil saturation, we use MOS equals to the flushed zone, water saturation of the flushed zone minus water saturation SW. Then we have movable hydrocarbon index. So movable hydrocarbon index can be estimated using the ratio of water saturation to the flushed, water saturation of the flushed zone. Then we have, we also have the bulk volume. So all these parameters could be estimated. Once we can determine our water saturation from the using the Archie's equation, then all these other parameters could be estimated. I think this is part of the assignment I gave you. Hello, is it part of the assignment I gave you? Hello?
What?
I said this is part of the assignment I gave you, estimating water saturation of the flood zone, water saturation of the, estimating water saturation. Yes, you said?
It's part of it, ma'am. Part of it, ma'am.
Yes, it's part of it, okay? And I also asked you to differentiate some logs, maybe gamma ray log, neutral density logs. So all the, I don't think there's anything in that assignment that is not in the material given. They are all there. They are all there. So, and if you are asked to calculate permeability, the formula is also there. Then fluid saturation. Like I said, when you talk about a fluid, it could be oil, it could be gas, it could be water. And there are some certain factors that can affect the fluid saturation. We talk about the pore structure, we talk about the fluid properties, we talk about the wettability. So this is talking about the wettability. So it could be asked that what is wettability? Is a measure of the tendency of a fluid to spread on a surface in the presence of a second fluid. So it is a function of the contact angle. So, and we have 4 types of wettability. We have the water wet, we have the oil wet, we have the neutral, then we have when it is completely wet. And it is also illustrated in the diagram there. When it is water wet, that is when the oil water contact, makes an acute angle. The oil water contact makes an acute angle. Okay, so when the angle is less than 90 degrees, when the wetting angle is greater than 90 degrees, we say it is all wet. When it is equal to 90 degrees, it is neutrally wet, okay? Then we have when it is less than 90 degrees, it is water wet. And when it is equal to 0, that is all water. You can see that it is parallel, okay? So I think this has been answered. The questions there have been answered. And likewise, I'm talking about the sampling of reservoir rocks, talking about the cuttings, the conventional core, the sidewall covering. I've talked about that. And why do we have to carry out our core analysis? It enables us to also estimate these petrophysical parameters. So apart from estimating these petrophysical parameters, we can validate with our log interpretation what we obtain for our porosity, our permeability, our water saturation, hydrocarbon saturation. Does it correspond with what we have in our log interpretation? And it's a direct measurement, you know. When we carry out the conventional core, you know, if we take the sample in such an undisturbed that can really give us a better information in order to reduce ambiguity in our interpretation, okay? So this is the principle of density. I think somebody asked me last week. So we can see our gamma rays is there, that it is being emitted, and it interacts with the formation, and from there, some of it is being attenuated. Then those that escaped is being recorded, picked by the detector. And when we have a low gamma ray count, that means that we have high bulk density. And when we have a high gamma ray count, indicates that we have low bulk density in the formation. Okay. So this is a formula for estimating estimating porosity from our density log. I think the equation is also there for estimating porosity from our sonic log. Okay. So if we are to calculate the sonic porosity, so some of these parameters will be given, most especially now that probably exam is going to be online based. So if it's going to be online based, that means you might not be provided with the well-log data to extract information from, and I don't know, I'll still need to discuss with Dr. Jyoti so that we'll know how to blend the two, you know, so that we'll ensure that to ensure maximum performance of our students. So we'll see how we can balance it all. So I think I also have to differentiate between the neutron log, induction log, and electric logs. Okay, the induction logs and the electric logs. What are the major differences? Okay, so this is just like the one I interpreted, that we have a gamma ray log low here indicating sand. We can see here we have a deep, medium, and shallow, and we can see varying responses of our resistivity log here too. And we can also see our gas here. We can see a decrease in the neutron porosity log. Okay. So this is the formula for estimating our water saturation. So when our N equals to 2, so we can see our water saturation equals to the square root of our formation, product of formation factor and resistivity of the water over the true resistivity. And I said our formation factor equals to 1 over porosity square. So here our A, when our A equals to 1, that is the tortuosity factor when it is equal to 1. And our M, it should be raised to the power, the porosity raised to the power of M, where our M equals to 2. So we have the cementation factor, you know, that is for Niger Delta environments. Okay. So this is the induction log, examples of the induction log and the electro logs. Okay, so you can see the differences are even there. The differences are there. Just have to pick them up. So I don't think you should have any problem. So like I said, the caliper measures our borehole size. And for our lithology logs, that is our gamma ray, our self potential, our gamma ray log. I think somebody also talked about the gamma ray log. So that can we use gamma ray log in a case O, okay? You know, I at the beginning I said that we have different time that measurements could be taken. Our measurements, our logs could be run while drilling the borehole. Our logs could be run after the borehole has been cased. That it could also be logged even when the borehole has been abandoned over a long period of time, you know, and even so they can reevaluate it. They can go there, go and run logs there again to see these parameters. Maybe there has been variation. Maybe hydrocarbons have accumulated a very long period of time, or even maybe some of these hydrocarbon zones could have been be overlooked during the exploration, you know. So many reasons why the why information could be retrieved. Various reasons why we could go back to the field and reevaluate, relog to measure these physical parameters to see the variation for whatever decisions that want to be taken. So our gamma ray log, you know, we say our gamma ray log can help us to identify our lithology. Then we have the spectral gamma ray log. That one has better resolution. That is the one that I said can give us the constituent contribution to radioactivity. That is the one that is being contributed by thorium, uranium, and potassium, unlike the gamma ray. And I think it has better resolution. The spectral gamma ray could be used in case O logs. And we know we should be able to also mention some examples of case O logs, you know, like our carbon oxygen logs, our inelastic logs. So we must be able to mention some of these post neutron. We must be able to mention some of these case O logs and some of these open O logs. When I ask you to differentiate open O logs, case O logs, you define them, then you tell us some of the examples in open O logs and some of the examples in case O logs. They're talking about our porosity logs. Yes?
Sorry, I didn't get the examples under each logs, open O and case O.
They are hot there in your material. They are hot there. I said carbon oxygen logs. They are hot there. They are there in that the material. The one this guy brought. What's his name? Giwa.
Don't say it now.
Let me open. Okay. We have the post neutron log.
Huh?
Post. PULSED, post neutron log.
Okay. That's for open O.
No. That case O.
Case O. Okay.
Yes. We have the carbon stroke oxygen logs. Carbon stroke oxygen logs.
For case O too.
Yes.
And elasticity log, I mean.
Inelastic.
Inelastic.
Yes.
For case O too.
Mm.
What about open O, ma?
Open O's, we've talked about them now. Your density logs, your porosity logs, your resistivity logs, your gamma ray logs, all those are your open. So there are lots of them. Check the material, you will see it there. The sigma, they are hot there. They are hot in the material.
Okay, ma. Thank you, ma.
Yes, you check your material for better information. So they are all there. They are all there. Okay. Then we talk about the importance of sonic log. Can somebody give me importance of sonic log? What we can use our sonic logs for?
And use our sonic log to affect porosity of the formation.
Okay. Is it only porosity of the formation? By using equation, we can be able to determine the porosity, okay? Is it only porosity that we can use our sonic logs to determine?
It can also indicate mechanical integrity of the reservoir rocks.
Okay, that we can use it to determine some elastic parameters. Some elastic parameters, that is our modulus, our bulk modulus, our shear modulus, our Poisson's ratios. They can, can give us information that can determine the strength, yes, the compressibility, how consolidated the formation is. Okay, is that all?
Estimate rock permeability.
Permeability.
The second
Porosity, but that porosity is basically primary porosity. Okay. Okay, what else again?
in combination with other.
You said?
In combination with other logs, it can also assist in identifying lithology.
Okay. Yes, to correlate with other logs to identify lithology. How? How can it help us to identify lithology? How? How can sonic log help us to identify lithology? Can you explain?
Because it measures the porosity of the rock, it's able to, or while the measurement is taking place, you're able to delineate the zones based on the porosity of the rock found beneath the subsurface.
What about because as a result of compaction, can it help us in the area of compaction? Maybe this area is non-consolidated, this space is unconsolidated. Can it help us in that area?
Yes, ma'am. Based on the travel time from the sonic log to the ground and back again.
Okay. So what will be the kind of response when we have consolidated formation and compared to where we have unconsolidated formation?
When you have consolidated rock, the travel time will be less because it will travel through all the pore spaces before it will come back. Then when we have unconsolidated rock, the travel time will be more. When you have consolidated rock, the travel time will be less.
And when it is consolidated, it will be less because it will travel faster. But when it is unconsolidated, it will take longer period of time. Okay. So what about what are the logs that we can use to determine our porosity log? Our porosity estimate. We want to determine our porosity using other logs. So which logs can we consider for estimating our porosity?
Neutron density logs.
Okay. Is it only neutron density log?
Sonic log.
Yes, sonic log can also help us in estimating the porosity of the formation. So resistivity logs, how can it help us? What do you use our resistivity logs for?
Good morning.
Good morning.
We use resistivity log to discriminate different fluid types in each formation.
Okay, they can help us to discriminate the fluid types. Okay, so like example of fluid and what kind of response are we expected to get?
Like in hydrocarbon, we are expected to have high resistivity.
Okay.
Because electric current does not flow well in hydrocarbons. While in water, we're expected to have low resistivity because electric current flow well in water. So the difference in the resistance to flow of electric current will help us to differentiate or to discriminate each fluid type in each formation.
Okay. Okay, thank you. So what log can we now use for our hydrocarbon typing? That is, we have established that, okay, this is a sand formation. In this sand formation, we have high resistivity. That is, it's most likely that we have hydrocarbon there. But now, how do we now know whether it is gas that we have in that formation or it is oil that we have there?
Neutron density log will tell us.
Okay, how?
Neutron density.
like the bubble or is it bubble effect? That
The
balloon
gas,
effect, rather. That
yes, the
balloon
Balloon
effect.
balloon
effect.
effect. Oh, okay, that is known as
Inflates
the gas effect. There will
Yes.
be decrease in the neutron density because of the low hydrogen content in the gas. So it gives that balloon effect. Okay, thank you. Okay, so I hope with that. Any other question?
Ma'am, please, can you please explain that gas effect again?
Okay, we'll do that.
Come, my laptop.
Okay, like here, like this example, so we can say that we have low gamma response here, so indicating that we have sandstone. Okay, sandstone, yes. Okay, so we have our resistivity log. So, and our resistivity we can see reading into the formation. Do you get it now? Talking about the bubble environment where we have the uninvaded zone. Do you get it now? So our deep resistivity is one that will give us the true resistivity. And you can see that it gives us the true resistivity of the formation. And we can see that we have high resistivity here, showing that the region has not been disturbed. Do you get it now? By the mud filtrate. So we can say that we have our very high resistivity there. And this response could indicate the presence of hydrocarbon. Do you get it now? So now, yes, it has been able to help us to differentiate. And if you look at this zone too, we are still in the sand formation. You know, whether we want to exploit for oil or we want to exploit for water, our target is the sand because it is porous and it is permeable. Do you get it now? And we can see the response here that it is low resistivity, so indicating that we have water there. Okay. So now coming to the neutron porosity, when we have oil or water, the neutron and the density, they tend to close up. Do you get it now? Okay. So, but for us to be able to know whether it is oil that we have there, whether it is water whether it is hydrocarbon that we have there, or whether it is water that we have there, our resistivity log can help us to discriminate that. Do you get it now? So now here that has been established that it is hydrocarbon that we have there. Now we want to now know what kind of hydrocarbon. Is it oil? Is it water? So assuming here it closes up, that shows that it is oil that we have there. Do you get it now? Okay, but because it opens up, there is a decrease in the neutron porosity log. Do you get it now? Because of the hydrogen content. You know, it is being bombarded by neutrons, and the rate of absorption depends on the kind of hydrogen content of the formation fluid. So for gas, it tends to have low hydrogen content. Do you get it now? So it will decrease. So that's where that balloon comes into place. This is not well open. You see some that it will open up to like 6. If you count the spaces, it can be up to like 5 spaces. So it will see the balloon-like shape. Do you get it now? Indicating the presence of gas. But when you see it closing up and it is the carbon zone, then it is likely that it is oil.
Oh,
Do you get it?
Yes, ma'am.
Yes.
Thank you, ma'am.
My question.
Okay.
Now, what if neutron is increasing and density is decreasing? What will happen? Like the other way around, like from the beginning part here.
Okay.
Neutron is increasing and density is decreasing. What can we say about that?
You know, like I said, that they are not stand-alone interpretation. You cannot just use this one to interpret alone.
Okay.
That is why we have other logs that you correlate with to establish that this is what is there. So it will not be misinterpreted.
So, but if it was here, like where the gas is now, what would we say is happening there? Is it possible?
Let's say that if our density is increasing,
yes.
If our density, if you look at it here, we have this is 1.65 to 2.65. So we can see that our density is increasing quite a lot. Density increases with depth.
Okay.
You get it down. Density increases with depth. But what happens to the neutron porosity? Do you get it now? When there is decrease in that neutron porosity, that is, it moves from the high to low. Do you get it now? That is where the crossover point comes into place. That is now the gas effect that probably is because of gas that we have there.
So you're saying that that cannot happen. Like it has to always be that the neutron would reduce.
No. There could be variation because of lithology. Lithology could change. So many things could change that could make the density to decrease or to increase. Do you get it now? But the normal trend is that the deeper you go, the higher the level of compaction, the higher the density. Density increases with depth. The consolidation increases as you go deeper. It gets harder. Do you get it now? But there could be variation in the lithology. There could be cracks. There could be anything that will bring change in that density. That instead of the density to be increasing, we are having the decline. And that is the ambiguity. That is the anomalous. Do you get it now? That's the area of anomaly that you now tend to be like, what could be the cause? Why do we have decrease in density there when it's supposed to be increasing? Then what are the other logs? What are the other responses? What are they saying? What could they be? That will guide your interpretation. Do you understand?
Yes, ma'am.
Okay. So,
Ma,
yeah.
I
Okay.
still don't know how to infer if it's oil, gas, or water from the neutron density log.
Okay. We said here that we have our sand formation. That is, we have our sand, so that is taken because of the low gamma response, right? Okay. So we can see this area that we have that is yellow, indicating where we have our sandstone. Do you get it now? And if you look at this interval, if you look at it also in your resistivity log, this is where it started from and it ended here. Do you get it now? That is where we have our sand. Now, in this sand, we don't know what we have in the sand. Do you get it now? Okay. Now, we have our resistivity log here. So the resistivity log can help us to determine the fluid type. Like, is it water? Is it hydrocarbon? Is it water or is it hydrocarbon? Now, we know that our hydrocarbon tends to behave like insulators. So, and insulators do not allow currents to flow through them. So if they don't allow current to flow through them, that means they have high resistivity. So if you check your resistivity log, the 3 logs here, they are all resistivity logs. Do you get it now? But the deep gives us true resistivity is more accurate because it gives us the resistivity of the undisturbed zone. So we can see here that we have very high resistivity. So that means it's most likely that we have hydrocarbon there. Do you get it now? Hello?
Yes, ma'am.
Okay. That is most likely that we have hydrocarbon there. But if we look at this zone below here, around 120 something to 130, you can see that we are still in the sandstone. Do you get it? But at this zone, we don't have high resistivity. The resistivity, but if you check, this is 2000, this is 0.2, and it is in logarithmic form. So and we can see that we have like 0.2. So you can see that it's very small. It's small, tending to 0.2. So the resistivity is low. So if the resistivity is low, that means there is high conductivity. Do you get it now? So if there is high conductivity, so that means it's not hydrocarbon. So that means probably it's water. Do you get it now? So here, this zone that we have established that we have hydrocarbon air, the resistivity has helped us to identify the fluid type. That is, it is not water that we have at this interval, it is hydrocarbon that we have at this interval. Now, what kind of hydrocarbon do we have? Is it oil? Is it gas? So we use our neutron porosity log and density log to establish if we have gas or oil. Do you get it now? So we have our neutron porosity log, which is the red. This is our neutron porosity log. And we have our density log, which is the black. Do you get it now? Okay. So now, in this formation, we can see that this is 60 to 0. Do you get it now? So we can see that there is a drop in this neutron porosity. Do you get it now? And that drop is the gas effect. So assuming it is high, it will close up like this with the density log, like our water. So the water response or oil response is similar. They tend to close up, but we can use our resistivity log to differentiate whether it is oil or water. Do you get it now? So this shows that this place is not oil, but it is gas. So usually, because of the gas effect, there's usually decrease in the hydrogen content in gas. So that is why we usually have something like vanilla-like. So I hope that is understood.
Yes, ma. Thank you, ma.
Okay. So I think we shouldn't have any problem with our assignment now. We should be able to go and do it and submit. Right? I've stated the formula that you need in calculating your flushed zone, water saturation of the flushed zone. What you need to calculate for your, the formula that you need to calculate your water saturated zones. So according to Archie, I've already stated it there. So you have it there. So you can bring out your parameters. Whenever you want to solve any question, you first highlight the parameters given. You state the formula, you highlight the parameters given, then you now substitute to get your answer. And your water saturation, they're usually in percentage, or you leave it in fraction. Okay? And I think we have discussed about this one, talking about porosity, effective porosity, total porosity, permeability, the absolute, the effective, and the total porosity. So some of the students have been able to even explain to us. Hello? Yeah? Hello? Hello? So I think you should spend more time with your materials. You go through them, go through your slide too, then try to solve, answer some of those questions, it will really help you. Any other question? So I think we are fine. We've come to the end of the class. So I wish you all the best.
Thank you, ma.
Louisa?
Are we done with your slide? Like, are we done with your side?
Yes, sir.
That's what you want to know. What do you think?
Yeah, done.
You are done. Okay. I will discuss with Dr. Dioti. So next week we will know. At least maybe we can lay our hands on some logs, try to extract information from the log, then input into those equations and calculate and all that. Because you should expect more of calculations in your exam test. We are still going to fix time for your test and all that. Okay?
Ma, you called my name.
Yes. I said, what do you think? You said you think we are true.
Ma, I think we are true, except you have something else.
Yes. I'll pass information across to you before the next class.
Okay, ma.
Thank you very much. Study very well. Okay?
Ma, is there any area of concentration?
I say you should read your material very, very well. Read your material very well. Then get past questions. Do you have access to past questions?
Yes, ma'am.
No, man.
No, ma,
No,
no.
ma, we don't
Not for
have
your
no.
course. Not for your course. Ma.
Okay. Maybe the class rep should see me during the week so that we get
You
questions.
know what to do.
You will make photocopies.
Yeah, you don't have
And-
Ma, you can always get soft copies now.
No, I won't give you soft copy, except in PDF form. Okay.
Yeah.
Yes.
Okay. I will discuss with Dr. Jyoti and I get back to you. So
Thank you,
ma'am.
if I send copies to
Gracias.
your class rep, then it will circulate to you guys.
Yes.
Okay.
Gracias.
Sorry, ma. Are we still supposed to submit those assignment the assignment as regards absolute porosity, the absolute permeability?
No, really. Make we.
I didn't put it on the platform. I didn't put it.
Okay.
Yes. So we should just read it.
So go and do the second one. That's on it.
That's better.
And prepare for your test. Okay.
When is the test, ma'am?
Okay. Thank you.